Welcome to this video on bacterial pathogens and superbugs. We will provide a comprehensive clinical and microbiological review covering toxin-mediated diseases, virulence factors, and the growing challenge of multi-drug resistant strains. In the first section, we will explore toxin-mediated bacterial diseases, focusing on the classical toxins, their specific cellular mechanisms, and the systemic clinical pathologies they produce. We begin with cholera, caused by Vibrio cholerae. This gram-negative motile rod is transmitted via the fecal-oral route. Its pathogenicity is linked to lysogenic infection by a bacteriophage that encodes the potent cholera toxin. The cholera toxin acts by ADP ribosylation, which permanently activates proteins and triggers adenylate cyclase. This results in massive fluid hypersecretion, leading to severe rice water stools. Management relies heavily on rapid oral rehydration therapy. Next, we examine Clostridium botulinum, an anaerobic spore-forming rod. It produces the most potent biological toxin known. This neurotoxin targets the presynaptic terminals of neuromuscular junctions, cleaving essential snare proteins and blocking neurotransmitter release. Botulism manifests in several forms, including foodborne and infant botulism. Clinical symptoms involve symmetric flaccid paralysis that can progress to respiratory arrest. Treatment requires antitoxins and often mechanical ventilation support. Diphtheria is caused by Corynebacterium diphtheriae. Its virulence is driven by a prophage carrying the tox gene. The diphtheria toxin functions by ADP ribosylating elongation factor 2, which halts protein synthesis and leads to necrotic cell death. Key features of diphtheria include the formation of a gray pseudomembrane and potential systemic complications like myocarditis. Vaccination via the DTaP or Tdap toxoid is highly effective, while treatment involves antitoxins and antibiotics. Enterohemorrhagic E. coli, or EHEC, is a major cause of hemorrhagic colitis. Its primary reservoir is the cattle gastrointestinal tract, and it causes intestinal injury through specific pathogenicity islands that create attaching and effacing lesions. A serious complication of EHEC infection is hemolytic uremic syndrome, caused by Shiga toxins that cleave 28-srRNA. Clinicians must exercise caution with antibiotics, as they can induce prophage expression and increase the risk of this syndrome. Scarlet fever is associated with Streptococcus pyogenes. Its pyrogenic exotoxins act as superantigens, causing non-specific T-cell activation and a resulting cytokine storm, which leads to systemic vasodilation and the characteristic rash. The manifestations of scarlet fever include pharyngitis, an erythematous rash, and the classic strawberry tongue. Resolution is achieved through antibiotic therapy, such as penicillin, which also prevents severe post-streptococcal complications. Moving to our second section, we will analyze antimicrobial resistance and superbugs, focusing on the molecular pathways utilized by pathogens like MRSA, ESBL producers, and carbapenem-resistant Enterobacteriaceae. The global impact of antibiotic resistance is profound, with millions of deaths attributable to or associated with resistant infections. This threat is exacerbated by factors like antibiotic overuse and the horizontal transfer of resistance genes. Finally, we look at MRSA. Resistance is conferred by the MECA or MECC genes, which encode an altered penicillin-binding protein with low affinity for beta-lactam antibiotics. This renders the organism resistant to most standard treatments. MRSA presents as two distinct types. Healthcare-associated MRSA often impacts immunocompromised patients, frequently carrying additional multi-drug resistance. In contrast, community-associated MRSA often affects healthy individuals and may carry the penton-valentine leukocidin toxin, which can cause severe skin abscesses and necrotizing pneumonia. ESBL-producing gram-negative rods are a major challenge. These organisms possess enzymes that degrade many penicillins and cephalosporins. These resistance genes are typically located on plasmids, which facilitates their spread between different species. Carbapenems generally remain the gold standard for treating these serious infections. Carbapenem-resistant Enterobacteriaceae, or CRE, represent an urgent threat. These bacteria produce enzymes like KPC or NDM, which neutralize nearly all beta-lactams. Bloodstream infections by these organisms carry mortality rates up to 50%, often necessitating the use of toxic, last-resort agents for treatment. Pathogens utilize several mechanisms to resist antibiotics. These include enzymatic degradation, where the drug is neutralized directly, alteration of porin channels or the use of efflux pumps to reduce drug accumulation, and the mutation of antibiotic targets to prevent binding. This matrix highlights key differences between common pathogens and superbugs. It categorizes them by gram stain, their primary virulence mechanism or toxin type, and standard first-line treatment options, emphasizing the diversity in clinical management. Combating these threats requires rigorous infection control, such as strict hand hygiene and patient isolation. Antimicrobial stewardship is also critical to prevent further resistance. Advances in rapid diagnostics and novel therapies, including phage therapy, provide hope for managing these resistant pathogens. In summary, bacterial pathogenicity is driven by powerful toxins and rapidly evolving resistance mechanisms. Addressing this dual crisis is a clinical priority that demands integrated efforts in surveillance, patient care, and the development of innovative therapeutic modalities. This concludes our video. We hope this review of bacterial pathogens and resistance mechanisms has been informative for your clinical studies.